Welcome to Understand Chemistry. This is Dr. Bilal with my fifth video of the series Free Radical Polymerization. In this video, we will understand the thermodynamic principles behind free radical polymerization. At its core, polymerization is a chemical equilibrium process where monomers are combined to form a polymer. This transformation is governed by the Gibbs Free Energy change, which tells us whether the reaction is thermodynamically favorable. At constant temperature, the Gibbs Free Energy for polymerization is given by the equation delta Gp equal to delta Gp naught plus RT log K, where delta Gp naught is the standard Gibbs free energy, which is defined as Gibbs energy of polymerization at standard condition of temperature and pressure. R is the gas constant, T is the absolute temperature, and K equilibrium is the equilibrium constant. But at equilibrium, delta Gp equals 0 because there is no net change in the concentrations of reactants and products. That simplifies our equation to 0 is equal to delta Gp naught plus RT log K equilibrium, which rearranges to delta Gp naught is equal to minus RT log K equilibrium, log K at equilibrium. This tells us that the standard Gibbs energy is directly related to the equilibrium constant. But we can go further since delta Gp naught is also defined as delta Gp naught is equal to delta Hp naught minus T delta Sp naught, where delta Hp naught is the enthalpy change, T is the absolute temperature, and delta Sp naught is the entropy change during polymerization. We can substitute and get delta Hp naught minus T delta Sp naught is equal to minus RT log K equilibrium. This final expression links enthalpy and entropy changes to equilibrium constant. It shows us that both heat exchange and disorder play a role in determining how far polymerization proceeds. A negative delta Gp naught means the reaction is spontaneous, and the larger the equilibrium constant, the more polymer is formed. Now, let us look more closely at the thermodynamic conditions required for a polymerization reaction to be spontaneous. The key criterion is that the Gibbs free energy change for the polymerization, denoted as delta Gp naught, must be negative. This means the reaction will proceed without external energy input. Mathematically, this is expressed as delta Gp naught is equal to delta Hp naught minus T delta Sp naught is less than 0. There are different possibilities of change in enthalpy and entropy, but here I will discuss only two of the most important cases that could lead to polymerization. Case 1, when delta Hp naught and delta Sp naught are less than 0 or negative. Delta Hp naught less than 0 means the reaction is exothermic. For exothermic reaction, energy is released because breaking the pi bonds in monomer requires less energy than forming the sigma bond in the polymer. So enthalpy favors the reaction. However, entropy works against it. We are going from a disordered system of individual monomer to a more ordered polymer chain. This decrease in or disorder means delta Sp naught is negative, and therefore T delta Sp naught becomes positive, which increase the delta Gp naught. To keep delta Gp naught negative overall, we need to minimize the impact of the entropy terms. That is why lower temperatures are favorable. They reduce the magnitude of the product T delta Sp naught, allowing the exothermic enthalpy change to dominate and drive the reaction forward. To sum up, we can say that in order to keep reaction going, we have to lower the value of T delta S by lowering the temperature. This means there must be a temperature above which the magnitude of T delta S is so large that the delta H naught value is not enough to favor the polymerization. That critical temperature above which polymerization no longer occurs. At this point, the rate of polymerization and depolymerization become equal, meaning the system reaches equilibrium. This temperature is called ceiling temperature. At equilibrium, change in Gibbs energy is equal to 0, for which we have previously found delta Hp naught minus T delta Sp naught is equal to minus RT log K at equilibrium. Consider a polymerization reaction at equilibrium. For this reaction, we can write the polymerization constant equal to equilibrium rate constant, which can be written as shown here. If we assume Mn radical is equal to Mn plus 1 radical, then we can write K equilibrium is equal to 1 over concentration of monomer at equilibrium, or simply we can write K equilibrium is equal to 1 over concentration of monomer. Placing the value of K equilibrium in the last expression, we get the expression delta Hp naught minus Tc delta Sp naught minus Rtc log 1 over concentration of monomer. On simplification, for sealing temperature Tc, we get the following expression. This equation shows that the sealing temperature depends not only the enthalpy and entropy of polymerization, but also on the monomer concentration. For standard concentrations, means for 1 molar solution, the term R log concentration of M becomes 0. We get Tc is equal to delta Hp naught over delta Sp naught. Let us look at a few examples. Styrene has a sealing temperature of 310 degrees Celsius, meaning it remains polymerizable at a relatively high temperature. Methyl methacrylate has a sealing temperature of 220 degrees Celsius. α-Methylstyrene, however, has a much lower sealing temperature of 61 degrees Celsius, making it prone to depolymerization at moderate temperature. So, understanding sealing temperature is crucial for designing polymerization processes, and it explains why some monomers are more thermally stable than the others. If the reaction temperature exceeds sealing temperature, the polymerization will begin to break down rather than to form. Now let's examine a less common but fascinating thermodynamic scenario in polymerization, where both the enthalpy change and the entropy change are positive. This situation describes an endothermic reaction with an increase in entropy. In other words, polymerization requires energy input, but it also leads to greater disorder in the system. This might sound illogical because we often associate polymer formation with increased order. But in certain systems, especially those involving rigid cyclic monomers, the story is different. Let us take elemental sulfur S8 as an example. The ring structure is highly ordered and rigid, with limited conformational freedom. When it is polymerized, the resulting chain contains SS bonds that allow for significant bond rotation, leading to a vast number of possible coiled and entangled conformations. This transition from a rigid ring to a flexible chain actually increases entropy. The transformation of cyclic siloxane into a linear siloxane polymer is another example of such system. Because the reaction is endothermic, that is delta Hp is greater than 0, and entropy increase means delta Sp is greater than 0, polymerization in this case is only favorable above a certain temperature, known as the floor temperature. Below this temperature, the reaction won't proceed. So unlike the sealing temperature, which sets up an upper limit, the floor temperature sets a lower threshold for polymerization to occur. This highlights how molecular structure and conformational freedom can dramatically influence the thermodynamics of polymerization. Thank you for joining me in the deep dive into the thermodynamics of polymerization. I hope it's sparked some new insight for your research or studies. Thanks for watching.